It is the part of the structure that transfers the load from superstructure to the subsoil safely. So it is the intermediate structure between the main superstructure, that is whatever the structure above the ground level is there, we call that as superstructure, to the soil. So this is an intermediate structure between the soil and the superstructure. We are having types of footing, so depending upon our requirement we'll be choosing one from this. Isolated footing, combined footing. So generally we can say isolated is, it is separated. So we are having the separate rectangular columns, we are calling it as isolated footing. So whenever we are combining these two columns, these two footings, we call that as combined footing. We are having raft or mat footing. So the mat foundation itself explains that is a closed mat. Okay, we are having a pile foundation, well foundation. This is depending upon the depth of the excavation, depth of the foundation. We are calling it as pile foundation, well foundation, or any technical terms that is pile is used in this. A well type foundation we are calling it as well foundation. Okay, here we are discussing about the design of the isolated footing. Okay, so I will explain you in detail with the steps first. Okay, coming to the design steps, remember we are having only 8 steps in this. So here we are having only 8 steps. Okay, so one by one I will be explaining you, and after that we'll also be solving some problem on this. Okay, given data, load acting on the column. So whatever the load that is acting on the column, see this is the footing, but we are having some column over here and the load is acting on this column. Okay, bearing capacity of the soil. Whenever we are talking about the foundation, we are talking about the column, that is the superstructure, whatever the superstructure that is present over this. And next we are also talking about the soil to which it has to transfer the load. Okay, so first of all we will be given all this FCK and FY, that is the yield strength of the steel and the characteristic compressive strength of concrete. Find the total load. So first step, see the first step is we will be writing all the given data. Okay, so the second step would be the total load. So in the next video coming, you can just give me some tips guys, like if you want me to simultaneously explain the steps and the problem, or first explain the steps and then go to the problem. Okay, just let me know in the comment section guys. If you want the simultaneous explanation, I will also be making a video on that. So but for now I will be explaining you the steps first and then we'll go to the problem. Okay, firstly we will be finding out the total load. See, as you know, we are given this the safe load, whatever the load that is acting on the column. We are firstly finding out the total load, that is P total. It is nothing but PU plus 10% of PU. Okay, PU is nothing but whatever the given load, the working load is there. See, as I have explained you in the video regarding the design philosophies of RCC members, I have explained you about the ultimate load concept. I will also be providing the link of that video, or you can just check out in the channel guys, the design philosophies in the design of the RCC members. In that I have clearly explained you the PU is nothing but the PW multiplied by some factor, whatever the load factor we are talking about. The load factor generally taken as 1.5. Okay, so here the 1.5 will be getting the PU. We will be given the load acting on the column, that would be the working load. But when we need the ultimate one, we are multiplying the working load with some factor, that is 1.5. So once we get the PU, we will substitute it in this. P total plus PU plus 10% of PU. Okay, the PU is the ultimate load. Ultimate load taken plus 10% of that ultimate load. That is nothing but the 1.1 times of the PU. Okay, the first step is writing the given data. Second step involves we are finding the total load acting on the footing. Next, calculate the area of the footing. So generally we are not considering the load acting on the see this is the column, but whatever the adjacent loads are acting, we are neglecting. So in that case, yes, we'll be considering the ultimate load, and also we'll be considering this extra load, that is with 10% of the ultimate load. So next, the third step is calculating the area of the footing. So using area is equals to, we know, so firstly let's tell you, stress is equals to force by area. We know this formula. So whenever we need to calculate the area, it's going to be area is equals to force by stress. Okay, here the force is nothing but the load that is acting. We know the P total, right? And here we are also be given with this safe bearing capacity of soil. that is nothing but the stress. Okay, so here from this formula we can just write area is equals to force by stress, that is P total divided by SPC, the safe bearing capacity of the soil, and decide the dimensions of the footing. So first of all, we are calculating the area of the footing. Once we got the area, we will be calculating the square side. See, we know square is nothing but here the area is breadth into breadth, because here the breadth is equals to depth in this case. So whenever we are talking about the square footing, both sides would be same. Area is nothing but B by B. So it's going to be B square. If area is B square, what would be the B? If area is equals to B square, what would be the B? B is nothing but the root A. Okay, so that is why it's root A over here. And we know the circular area is nothing but the pi d square by 4, where d is the diameter of the footing, okay, the column. Whatever the load that is acting, for that we are deciding this footing. Okay, so here the circular footing, if we want to provide a circular footing, substitute in this, you will be getting the diameter of the footing. In this if you substitute the formula, you will be getting the square side. Whatever the side of the footing is there, we will be getting. In the rectangular one, we will be getting L by B is equals to A. Okay, so here remember L by B is equals to D by B of the footing. So here using this relation, we will be getting one term, and substitute the other in this, you will be getting the second term also. Okay, L by B is equals to D by B. I'll explain you what is it in detail while we are solving this problem. So in the previous step, we decided the dimensions of the footing. So now we are determining the net upward pressure intensity. Remember, it is nothing but NUPI. So we are determining it using this formula. Again, the stress is going to be the force by area. So using this, we will be determining the net upward pressure intensity. That is, see, whenever we are talking about the load that is applied downwards, we know some forces would be there that would be lifting it upwards. Okay, so whenever we are designing the footing, we should also be considering the upward intensities, upward pressure that is coming. So here we are designing it for the downward load, but we should also be considering the net upward intensity. Whatever the tendency of the soil to uplift the footing is there, we should also be considering that. So here we are considering not only the dead load that is acting downwards, but also the net upward pressure intensity that is applied from the soil to the footing. Determine the maximum bending moment at the face of the column as per IS 456-2000. I will explain you in detail using the IS codal provisions. So after that, we can just get into this. Determine the thickness of the footing and area of the scale in both directions. So we firstly understood what would be the dimension of this. But coming to the depth, so this is the cross section. From top view, we are just mentioning this. But whenever we are talking about the depth of the footing, that is the other side, the bottom side of this will be there. Here we are determining the thickness of the footing and also the area of steel to be provided in both directions. Check for one-way shear, that is the beam shear, using the IS codal provisions, and that the critical section occurs at depth D, distance D from the column, and check for the two-way shear. See, very important guys, whenever we are discussing about the footing, we have to do the check for both the one-way shear and two-way shear. Remember, the one-way shear is called beam shear, the two-way shear is called punching shear. One-way shear, beam shear. Two-way shear, punching shear. It is very important, asked in many competitive exams already. So here we are using IS codal provision, and the one-way shear, the critical section is the distance D from the face of the column. From the face of the column, not the footing. See, this is the footing, on top we will be having column. So from the face of the column, we are considering it as D. Okay, this would be the one-way shear, the critical section for the one-way shear. And for the two-way shear, it is at a distance D by 2 from the face of column along the periphery. See, periphery from the edges. So from the edges, we will just be leaving the distance D by 2 from the column. Here, remember, it is at the distance D from face of column for one-way shear. At a distance D by 2 from the face of the column along the periphery. So I'll be explaining you with figures once we get into this problem. Remember, just roughly I'm explaining you. Firstly, in step 1, writing the given data. Second one, we'll be calculating the total load that is acting on the footing, and next from that we'll be getting the area. We'll be deciding the side of the footing, the shape first, and next comes the dimensions of that. And after that we'll be determining the net upward pressure intensity, the maximum bending moment acting, and depending on that bending moment we'll be considering all the factors, and we'll be determining the thickness of the footing, the reinforcement details. And once the reinforcement has been provided, has been designed, then we'll go to the checks. Okay, if it is good, it's okay. If it's not, we'll be redesigning the structure. Okay, so let's go to the designing part now. Design an isolated RCC footing for a rectangular column of size 230 by 380 mm. So here we are given the column dimensions, as I've already told you. Carrying a working load of 500 kN. The safe bearing capacity of soil is also given, FCK, Fy. Okay, as I've told you here, we'll be given the load acting, safe bearing capacity of the soil, and FCK and Fy. Okay, all these are given over here. Firstly, writing all the given data that has been provided. Step 2, I've told you we will be calculating the total load, PU plus 10% of PU. Remember, here we are given the working load. We have been given this working load. I told you we have to calculate the ultimate load by multiplying the working load with some factor called load factor, that is generally 1.5. So we got the ultimate load. Substitute in this equation, you will be getting the total load that is been acting on this. Okay, this is the total load that is acting on the footing, to which we have to design now. So step 3 is going to be the area of footing. As I already told you, stress is equals to force by area. Now we need area. Area is going to be P by stress. P is nothing but the total load which we have calculated in the step 2, and safe bearing capacity is given in the question already. So that's going to be the area, and we have to be designing it. As we have given, we are being given the rectangular column. We are considering the rectangular footing over here. That's going to be area is equals to length into breadth. We know the L by B is equals to capital D by small b. So this is nothing but the dimensions of the column. Okay, from the dimensions of the column given, we'll be calculating this. See, initially we are given this L by B, B by D, the depth of the section. So in this column, we have been given the capital D and the small b. B is nothing but the width of this. Okay, width to depth. So depending upon the width to depth ratio of the column, we'll be analyzing this and we'll be getting the dimensions of the footing. So L by B is nothing but capital D by B. So it is the overall depth, D is the overall depth, B is the width of that. So from this we'll be getting the relation L by B ratio. Substitute this in the area formula, you'll be getting L by B. So here finally we have got the dimensions of the footing. Okay, I told you firstly we'll be analyzing the downward loads. So whatever the downward loads are there, for that we are providing this dimension. The cross section of footing has been decided. Now we have to go to the net upward pressure intensity. Whatever the upward pressure from the soil has been exerted on the footing, now we will be calculating that. W is equals to PU by A. Here we know PU is nothing but the ultimate load, which we have calculated in step 1 itself. In the given data we have calculated PU. Area we got now. So whatever the pressure that has been exerted on this footing, firstly we'll be calculating the dimensions of the footing. To that footing we'll be checking the pressure intensity. You'll be getting some W value. So NUPI for 1.7 meters wide. See, for 1.7 meters width we are getting this. Okay, so first of all, whenever we are talking this, it is per meter. Okay, whatever this is there, it is per meter, but we need it for 1.7 meters. So it's going to be this value multiplied by 1.7. You will be getting the total net upward pressure intensity. Okay, first of all, we have to do this. Next, we are calculating the bending moment. Here the bending moment formula along the x direction we are taking as Wx square by 2. Along the x direction, that is why we are taking x square. If it is y square, if it is along the y direction, you will be taking the y square. Okay, maximum bending moment, it is going to be Wx square by 2. What is this x now? We know x is nothing but this distance. I will let you know what is this. 2.8 is nothing but the footing width dimension. Along x whatever, see this is 2.8 and 1.7. Okay, and in this we are having the column has also been provided, so that is going to be of 230 by 380. It is given in question already. Okay, this is the dimension of the column. Okay, here whenever we are designing the footing, we know the column is somewhere in between this. Okay, so in the center we are having column. See, 2.8 is the maximum length side, that is the greater length side, so obviously the 380 would be coming over here. In 230, this would be 230 mm. This is 2000, 280 mm. Okay, so in this, whenever we are talking about this larger side, it's going to be 2.8. This 2.8 minus 0.38. Writing everything in meter. Okay, 2.8 minus subtracted by this 0.38 divided by 2, because we just need this small part. So to get this smaller part, from this we are firstly removing the column, so all the two sides would be left. So whenever we are dividing it by 2, we'll be getting only the one side length. Okay, I think now you understood. See, firstly along this length we are subtracting the column width, so the remaining would be this, right? So whenever we are dividing it by 2, you will be getting the one side width. Okay, this width. To get this, we are doing this. Okay, once we got that, MUX would be W, X is this value, X square by 2. This is MUX along X direction. Similarly, along Y direction, if you need this one, it's going to be 1.7 minus 0.23. Minus 0.23, you will be getting all this value. So again, if we divide it by 2, you will be getting this small value from here to here. Okay, so it's going to be MUY, WY square by 2. Y is this one. Okay, so we got MUX and MUY. So for MUX, this is the formula we know as per IS codal provisions. So this is generally provided in the NXD code of this IS 456, and if you substitute everything in this, you'll be getting D. This is the thickness. However, accounting for the one way and two way shear provide this much. So if it is 202, just increase it. Okay, almost double it. Okay, so with the cover, we will also be deciding the cover. It is randomly taken. Choose any value. Generally 50 mm is chosen one. Next, we are calculating the area of steel. Remember, first one we will be taking the MUX and MUY. In this, see, MUX we got 192, and MUY we got 72. So the greater moment, we will be considering this. So whenever we are calculating any thickness or these values, you will be taking the maximum one, the greater moment, because if we are designing it for the greater moment, it can take any value in between that. Okay, it can take any value, but whenever we are taking the lesser one, if it is subjected to the greater moment, it will fail. So that is why we will be considering it for the greater moment. Okay, whatever the greater of the MUX and MUY value we have got, take that one over here. Calculate the thickness using this formula. Don't forget, this is very important. It is provided in the NXD of IS 456 2000. Okay, next, area of steel. This is formula. Even this is provided in the NXD. Okay, this is going to be the NXD, MUX. Substitute everything in this, you'll be getting AST. Select the diameter of the bar as per your choice. So here I have taken 12 mm diameter. This is the formula just to calculate the spacing. So along the ASTY, using this formula, you'll be getting this see, along X direction, along Y direction. Depending upon our requirement, we'll be selecting this. Okay, so here, depending upon your requirement, we are selecting 12 mm dia along the X direction, 10 mm dia bars along the Y direction. Here we are having the check for one way shear. The critical section occurs at a distance of D from the face of the column. See, I've already told you, we know the small d, the effective depth value. Considering the effective cover, we have just taken this 350 mm. See here we have calculated, using this formula we have calculated the small d and capital D, effective depth and the overall depth. So for this effective depth we are analyzing this. So it's going to be NUPI into shaded area. Whatever the shaded area is nothing but the critical section, that is at a distance of D, the small d value from the face of the column. See, from the distance 350 mm, whatever the other distance, this is the section that is shaded. This would be the critical area for the one-way shear. Okay, the shear force is nothing but the load in the shaded area. We know the load is nothing but the stress multiplied by the area. We know the NUPI, we have calculated it, multiplied by 1.7 because we have to calculate for the 1.7 meters. It is per meter. So it's going to be 1.7 multiplied by this, multiplied by the shaded area. See, this is shaded area. Whatever the overall length is there, in that we'll be subtracting this 350 mm. This is the shaded area distance. Okay, so here the shaded area is nothing but 1.7 multiplied by 0.86. This is the 1.7 value, this is 0.86. So this area multiplied by the net upward pressure intensity, we'll be getting the shear force. Force is nothing but stress multiplied by area. The nominal shear force, see, this is the ultimate shear force we have calculated. Next, the nominal shear force as per the IS codal provisions is going to be the ultimate shear divided by area. The ultimate shear we got here, substitute in this, B by D, we know the value. B is this, D is the small value we have got. Okay, B is going to be 1700 mm. We know the tau VU. So, using the IS codal provisions, we can calculate the permissible shear stress. So, whatever for M20 value, we know the percentage is nothing but AST by BD into 100. This is the formula. Okay. Remember PT, the percentage of the reinforcement is going to be AST divided by BD, the overall section. Whatever the percentage of reinforcement is provided for the overall section, this is the value. PT by BD into 100. We got the PT. So using the table 19 of IS 456, which I'll be showing you now. So here, see, this is the table which I was talking about. The design shear strength, tau C is nothing but depending upon the PT, that is area of steel, the percentage of steel provided, that is AST by BD into 100. So here we have got the PT value as 0.32%. So 0.32, we have just find the value, which is the 0.32 is between which value. See, over here we can see we are having the AST by BD into 100, we are having 0.15, 0.25, 0.575. We got the value of 0.32, that is in between 0.25 and 0.5. So we are designing it for M20. So check this. Okay, 0.25, 0.5. It is 0.36 and 0.48. Take the value. Note down it. Okay, 0.25, 0.5. For this, whatever the tau C value is there, this is tau C value. For the PT value. So this is the PT value, 0.32. So if for 0.5 this is the value, for 0.25 it is this, and we have to now find out what is the value of tau C for 0.32. So there is some formula, guys. We'll just be finding out the differences. I'll be providing you the interpolation formula. So it's going to be, firstly find the difference between this, that is 0.5 minus 0.25, 0.48 minus 0.36, and after that we will just be interpolating it. Even in Google the interpolation formula has been provided, guys. You just have to find the differences and just cross multiply that. Okay, 0.07, whatever the difference between these values is there, that is been provided. You just have to add with the add for this reference value. Whatever the reference value you have considered, take that one. Okay, remember the tau V value which we got over here, the tau V value, that should be less than the tau C, because this is a design shear strength value. Tau C is nothing but the design shear strength. So however, only if this condition is satisfied, we can say the structure is safe in one-way shear. Okay, only in that case we can say the structure is safe in one-way shear. Next, let us see if it is safe in two-way shear. For this, the critical section is different again. So here the critical section is small d. It is the distance of small d from the face of the column. Now along the periphery we have to find out that. I will tell you. critical section occurs at a distance d by 2. D by 2 is nothing but the effective depth divided by 2 along the periphery of the column. See, as per the IS codal provision, this is in the page number 58. Page number 58, and remember the table we have used for calculating the tau c value is table 19. Table 19 of IS 456. And here, as you can see, it is in the page number 58. The support section column for the footing, the critical section is at a distance of d by 2 from the face of the column. Okay, distance d by 2 along the periphery. Along the periphery, that is along all the sides, you will have to just calculate the d by 2 value. See, this is the column. You just have to draw this. This is the plan, guys, and at a distance d by 2, you are just specifying some section. Okay, around the column at a distance d by 2, you are just projecting some section over here. That is going to be the critical section. Okay, here the shear force we are considering is the punching shear. So the formula is, we need this for to calculate the force, we have to multiply the stress multiplied by area. We have to get the value of the force. That's going to be Pu minus Nu Pi. So this is going to be the stress, guys. Whatever the Pu minus the Nu Pi, this is the value of the stress multiplied by the area. So you know how to calculate the area. 0.73. See, firstly, the 750 minus 157.56 into 0.73. This is 0.73 and this is 0.58. In the whole thing, we are again dividing the taking out this part. That's going to the VU. VU is Pu minus Nu Pi into shaded area. This is the formula. Calculate the VU. Okay. At a distance d by 2. To get this value, 0.38 plus d by 2 plus d by 2, because both sides. Here we are having d by 2, here we are having d by 2. Okay. Next, you will be getting tau VU. Again, here we are having another formula to calculate the permissible shear stress. It is in the page number 56. I will show you. See here, the permissible shear stress, we are having this formula. Some factor multiplied by tau c. Here, this is the formula, guys. Here, whenever we are talking about the BC, here the beta C, remember this shouldn't be, this Ks shouldn't be greater than 1. If it is greater than 1, take 1. Okay. This is the dimension we are considered. I will show you this diagram. See. This is 380. The column side. Okay, so here the column dimensions we are considering. Whenever we are talking about beta C, it's nothing but the ratio of the shortest side of the column to the longer side of the column. See, if it is 230 by 380 mm, this is in mm. Whenever we are talking about meters, you just have to divide it by 1000. Okay, so 0.23 divided by 0.38, you will get the value of Ks. If it is greater than 1, take it as 1. Okay, if it is greater than 1, take it as 1. This is the Ks value. Next, tau c is nothing but 0.25 root FCK. 0.25 root FCK. FCK of the concrete is considered. For M20 we are designing, take it as M20. You will be calculating the tau c. See, remember, tau c should always be greater than tau v, because tau v is nothing but the load that is acting, and tau c is the value for which we are designing. Whenever we are designing, we have to design it from greater value than that is subjected to. As the tau c is greater than tau v, it is safe in two-way shear. Then we are just drawing this diagram. However, along the lateral direction, along the longitudinal direction, along the longitudinal, this is the longitudinal along the length, this is the lateral dimension. So we are calculating all this. So we have calculated along the x direction and along the y direction. So according to this, we have to project all the reinforcement details on this figure. Okay. So with this we have completed the detailed design of the isolated RCC footing. Okay guys, everything in this is clearly explained. Still, if you have any doubts, do let me know in the comment section. That is it for this video, guys. If you like this video, please like, share and comment the channel, and don't forget to subscribe my channel, guys. Thank you for watching this video.